fairly straightforward. This is a little bit less straightforward.
Did you define what the autonomous system is?
No, I can discuss that briefly. So we have our system of ordinary differential equations, which we have written this way. If we say that f is only a function of the independent variable, then this is an autonomous ordinary differential equation.
I think this is called dependent variable. T is independent.
Yes. Dependent variable. Y is a function of t. And this has lots of qualitative properties in terms of we can shift things by t. We can change our initial time without at all modifying what the equation says. So in some sense, you can talk, once we get to vector flows, you can say that the flow is the same no matter what the initial time is. It has other qualitative properties, and this concept does generalize to partial differential equations in terms of both time and spatial dependence. Yeah. So this is section, I forget, section 3. As far as I'm aware, this particular theorem is not discussed in any class of tech that I've taken. So not in 471 or geometry or any other courses. So this may or may not be new to anyone.
Well, we do it in geometry, but there isn't, I don't
we
prove
do
it.
geometry, yeah.
Because we use that all the time.
Okay, so I'm going to also, and this is not in the book, so I'll have to remember this notation. I'm going to talk about the neighborhood of a point being the set X Is this the correct definition of a neighborhood?
No.
Okay. So the neighborhood of a point can be seen as sort of points nearby, the distance that they have to be from each other. This can also be generalized to arbitrary metric spaces. This was what I was saying was the distance function. Distance within epsilon. And that will simplify this notation. Okay. So we have this map from a neighborhood. Let's see. Okay. From a neighborhood of a point to Rn, and this point is itself in Rn. So this is a map from the neighborhood of a point to the rest of Rn.
Well, why do you say to the rest? It's not to the rest, to the whole.
To Rn, right, sorry. We assume that f is ck, meaning k times differentiable. Right, he calls it a ck map. So this has k derivatives of all mixed kinds. And each one is continuous. We assume that the derivative, or the Jacobian of this transformation, this mapping, is invertible. So again, if we're dealing in finite dimensional spaces, this is a matrix. We know all the invertibility criteria for when a matrix is invertible.
Invertible right? At the point, at any point, or at point P0? Well, if it's continuous,
he just says invertible, right? So
if it's continuous at P0, then it will be continuous in a neighborhood,
right.
Invertible in a neighborhood. Yeah.
So this map might be more generally defined, and the whole point of restricting it to this neighborhood is to say that it's invertible at this neighborhood. So an equivalent definition would be to say that this is a map from some larger set, and say that it's invertible at that point, and therefore in a neighborhood of that point. Both definitions are kind of equivalent, right? Does that sort of make sense?
Well, I don't think that the second one is true. I mean, this is only local invertibility.
Right.
Even if the Jacobian is not 0, you may not have global invertibility. I mean,
Right.
you could have Jacobian where it's everywhere invertible, and still it is not globally invertible.
Well, what I'm saying
is only
is
defined on the neighborhood, so.
Yeah, that's why. But he said it could be a larger set.
this could be a larger set, but then we say invertible at P0. Right? We could change this definition to put a larger set here, but then qualify this term invertible. Right? And I'm saying that's equivalent. But anyway, I'll move on. So then we have another neighborhood. Right. So we have another neighborhood of, say, P0, and a neighborhood of Q0. And it doesn't define where Q0 is. I'm assuming Q0 is just any point of Rn. Oh, right, Q0 is in the image of this neighborhood. Q0 has to be in that image. I should keep my notation straight. So it is a bijection.
Okay, where you said suppose, where is this statement? Then you need to say.
Right, if we suppose, okay, yeah.
Then, okay.
Right, so if we assume that this Jacobian is invertible, then we talk about the image of this neighborhood in Rn, and what we say is, this has to be a bijection, and the inverse of this bijection, being defined from the other direction, is k times continuous.
K times continuous the differential.
Differential, sorry.
Basically, what it says is that if a map is defined in a neighborhood of a point and the Jacobian is non-degenerate at that point, then there exists a neighborhood where it is invertible, like this bijection. But it's only local.
So if Q0, of course, is this map applied to P0, it's saying that if this is k times continuous, k times differentiable, continuously differentiable here, then we can define the inverse map of this. It's bijective, we can define an inverse, and this will be k times differentiable. Does that make sense? Does that not make sense? No. Okay. So anyway, I believe his use of this is to prove the implicit function theorem, which is slightly more general, and we don't have time for it. There's a class here in a few minutes. But the implicit function theorem is the same condition. If the Jacobian